Good evening or good morning, everyone. Welcome to this new webinar. As you know, this new webinar will be on the new features we introduced in STKO version 4, which has been released a few weeks ago. As I said, for those of you who are here, unfortunately, we couldn't start the live streaming on YouTube for some reason with Zoom. But anyway, we have a local recording. So local recording will be made available by tomorrow, together with the presentation and all the files that we will use today. Okay. Perfect. So let me share my screen. Okay. Okay, so just before we start, by tomorrow you will be able to download the recordings and all these files, the presentation with the new features we have in STKO 4, and some of the files that I will use to explain them. Okay, so let's go to the presentation first, and okay, let me move this one. Okay, so here we have a list of okay, here we have a list of the new features we have in STKO version 4. And of course, if you want to use them, you also need the latest version of OpenSys, which currently is version 3.7.0. So we have some new features that are only related to STKO. Some of them instead are also related to OpenSys. I will not talk about all of them. These ones here are features that have been already discussed. The new triangular shell element has been discussed in a couple of webinars ago. The same for the ASD coupled hinge, and the same thing for ASD plastic material. There are a few other new things that we are still working on, so I will not talk about them. When we will finish the beta testing on them, we will prepare webinars. Okay, so the first thing I want to show you is about some of the new features which are only related to STKO. Okay, so if for the first three, you can find examples here in the folder 01 GUI features, which is the first one. Okay, here you will find a single file and the post-processing as well, and I will use it to show you what we have here. Okay, so if I open the first file in GUI features, okay, this one is a simple benchmark test of a pinched cylinder. I think I used this one in the previous webinars about shells when I was explaining the co-rotational formulation. So I will not go through the examples, but in this example, what we have is 1/4 of the entire cylinder, okay? And we take advantage of symmetry. Now, the first thing that you will see in STKO, if you open a previous file and you were modeling with shells and you go under property, you will see that now you have a section extrusion. So nothing changed, it's just the visual representation, okay? So before, the only extrusion was available for beam elements. Now you also have extrusions for shell elements. So this one is only a pure visualization stuff. But one thing that is quite important is this point here in post-processing, because many times you have you model taking advantage of symmetries, for example. But when you want to produce a plot or an animation in post-processing, you may want to see the entire structure. Okay, and so what we did in STKO, and if you want, you can directly open the post-processing file that we have here. So you can go under open, and you can open the SPD file, which is the file for post-processing, which will already load everything. So as you can see now, I prepared in this file different plots. So the original one is only this one, okay, which is actually the file that I used, which is the real output from OpenSys, okay? So I have only 1/4 of this cylinder, okay? Now let's say I want to represent the entire structure. What I can do is to create other plots, and as you can see, you can apply a transformation to them, okay? Now in this case, I applied a mirror, where the mirror plane is the 0, 1, 0, so the local y-axis. and then a few others, okay? So in this way, you can have the entire plot. Then in a while, I will show you how this transformation works, okay? Keep in mind that they are not actually duplicating any memory in the output database. It's just applying plain transformation to a plot, to an existing plot, okay? And of course, when you do this kind of things, you may want to switch off all these color bars because they are not necessary. So you can take only the one from the first one, okay? So if you want, you can switch them off and on. And of course, when you will go in the output here in the animation, when you try to slide it, you will see a little delay between them, but it's just because we are running the rendering in parallel, so they are not synchronized. But if you do the video of the animation, they will be synchronized, okay? So let me go, for example, to the beginning. Let me make it a little bit faster. Okay, so now you can do the animation. You have just saved 1/4 of the model, but you can visualize the entire model. Some other features that we didn't have before is the first step for the animation, or for example, if you have a lengthy analysis and you don't want to render the entire analysis, you can add a step. For example, now I want to see a video every 10 steps, so it can be faster and the output can be less expensive. Okay, so this one is one of the nicest new features in the STKO post-processor, and now I want to show you how the transformation works. Okay, so in this file you have the complete example. Now let me just without saving this file, I want to do it from the beginning. Okay, so what you can do now in a plot, if you create a new plot and you go under the editor, down at the bottom, you have this new table here, which is called transformations. Okay, so by default, it's empty. Okay, so there is no transformation to the original plot. If you right click here, you have some presets. For example, I want to add a scale transformation. Okay, in this case, you have a vector, which is the scale factor in X, Y, and Z. Okay, so by default is 1, 1, 1, which means I'm not transforming anything. If I double click on it, for example, I want to scale it about the X-axis. Okay, I can put 2 here. It will be twice as long in the X-axis. Keep in mind that every transformation starts from the center, okay, from the origin. Okay, so for example, in this case, you have a scale. I can remove it. Let me, for example, try to do a rotation. For a rotation, you have an axis of rotation and rotation angle in degrees. So for example, let's say I want to apply a rotation of 45 degrees about the global z-axis. Okay, I can put 0, 0, 1, and I can put 45 here. Okay, and so as you can see, if I go on top, okay, I apply that 45 degrees from the center here. Now, let's say after the rotation, I want to translate this point here, and this distance is 100 units. Okay, so I can add another transformation that can be, for example, the translation, and I want to translate in X of 100 units. Okay, so now you have first a rotation and then a translation. Now, as you may know, transformation matrices, they are applied in a certain order. So in this case, I first rotated it about the center and then I translated it. Of course, if you change the order, like for example, if I drag and drop the transformation before, you will see a different output because now first the model has been translated here and then it has been rotated 45 degrees about the center. So the output is different, of course. Okay. Now, let me just, so you can play with them and try to understand how it works. So we have seen the scale, translate, rotate. Well, there is a mirror, which is the one that I used in the example file. For a mirror, you have to specify the normal of the plane with respect to which you want to apply the mirror. So let's say I want to mirror this one on this other side. The normal will be the y-axis. Okay, so if I put a 1 here, which is the global y-axis, it will be mirrored on this side. Okay. What else? There is the mirror and there is the custom one. Okay, so if you want to apply a custom transformation, then it's up to you on what you're entering. Okay. So now you have a 3x3 transformation here that takes care of rotation and scaling. And the 4th column here is for translation. Okay. So for example, in this case, I'm not applying any scaling. If I put a 2 here, I will apply a scale in X. But in this way, you can do custom things. So for example, I can do a shearing, like the Y displacement will be equal to the X displacement. In this case, you're applying a shear deformation to your plot. So you can play with it and you can create custom transformation. So the concept is you can take the original model and you can apply transformation to them. You can duplicate it and you can assemble a complete model. This is also useful sometimes when you are comparing the same output from same files which are located on the same position, but you want to put them one after the other with a certain spacing to do some comparison. Okay. So this is fine for the first 3 points. Now the next point is about the ASD Concrete 3D. Now we added few new features that are not strictly necessary for concrete because these parameters were not available before because we had hard-coded them inside OpenSeas with values that were optimized for concrete. Then people started to use it, for example, for masonry, and because masonry is a concrete-like material, not exactly the same, but it's a concrete-like material. And people started using ASD Concrete 3D in place of the old damaged TC 3D. And sometimes they noticed that for masonry, it was quite overestimating certain behavior. So we introduced these factors that can be calibrated when you want to use ASD concrete, not exactly for concrete, okay? And in this example, I will be using the example that you can find here in 0.2 ASD concrete features, which is this one, okay? What I'm doing here is exactly micro modeling of masonry. So I will be using the ASD Concrete 3D for bricks and mortar joints, okay? And I will do a monotonic test and a cyclic test, and I will compare the different models, okay? So let me close this one. And let's open example 2 ASD concrete features. Let's start by the monotonic one. So I will try to explain what's the difference. So also here, as you can see, the model, I already made a webinar about this micro modeling with masonry, and it was using the damaged TC3D model. Then people started using the ASD concrete 3D because behaves better in cyclic condition, but it was too much optimized for concrete, and it was overestimating the strength of masonry structure for one particular reason, and then I will explain it to you. So this was made with shell elements. So you have cross sections, and that's why if you go in property now, you will see the section extrusion, but it's still the same model as before. So let's go here in the XY plane. Here you will find 3 different models, which are actually the same. I only changed the material properties. So what I've done is to use, well, first of all, this is a micro modeling approach. So we are modeling bricks and mortar explicitly. So we have 3 kinds of sections, the steel section at the bottom and at the top, but then we have bricks here and mortar joints, okay? So for the steel section, we are simply using an elastic membrane plate section, so nothing special here. For bricks and mortar, we were using, in the first example, in the original example, we were using the damaged TC3D, okay? And then, so what I've done is to use the same model that I had before, damaged TC3D, and for brick and mortar, and I called them brick old and mortar old. And then I created a new one, both for brick and mortar, using the ASD concrete 3D material, using the default parameters, because before you didn't have these 2 parameters. Now, this one is not important, is only useful in 3-dimensional analysis, but in this case, we have shells. So in shell element or in plane stress element, this parameter does not apply. While this one is important because it affects the dilatant behavior of this material. So at the beginning, the default value was 0, and you couldn't change it because it was optimized for concrete. But now what happens when you try to use this one for masonry in a micro modeling approach? Now in a micro modeling approach, and I've already talked about this one, if you use a plane stress assumption, like in this case, because remember, we are not using solids, we are using shells. if you use shells or plane stress element, the out of plane stress, the sigma 33, will always be 0, okay, by assumption. The problem is that in reality, when you do a micro model of masonry, or what happens in reality is that you have this thin layer of mortar, which is not so strong in the uniaxial compression test. For example, this mortar can have like 3 megapascal of uniaxial compression. But due to the fact that this thin layer is packed between two bricks, which are much stiffer than the mortar itself, it produces a state of triaxial compression inside the mortar layer. And so in a state of triaxial compression, the mortar will exhibit a higher confined compressive strength. The problem is that when you use a two-dimensional model or a shell model, you cannot capture this effect because by default you will never have a compressive out of plane shears, out of plane normal stress. Okay, so typically what people do in this kind of scenario, they take the mortar, which is here. So instead of giving it the compressive strength of the plane mortar, they give the confined strength of the mortar. Okay, so now what happens is that instead of using the original one, you're actually using a non-physical higher strength for mortar, and this increases both the friction angle and the dilatancy angle of this material because you cannot directly control the dilatancy angle. So what we did now is to introduce a new factor that you can change to match the dilatancy of that material. Okay, so just to explain what I'm doing here, the initial material is this one. The mortar new is the plane translation from damaged TC3D to ASD concrete 3D. Okay, which by default has a CFD, which is the cross damage factor, which is the parameter that will control the dilatancy, which by default is set to 0. So it's, let's say, the one that gives the dilatancy of a concrete material. Now, if I use this one, you will see that these overestimate the shear strength of the masonry wall because it is, in this kind of example, I first apply a vertical compression, then I fix the vertical displacement and apply shear. This is the kind of simulation that we are doing. So if you overestimate the dilatancy of your material will show a higher shear strength, which is non-physical in this example. And what I've done here is mortar new CFD is basically the same as this one, as mortar new. The only thing is that I've changed the cross damage factor. So the idea here is that you can calibrate this one, but technically what I do is, for example, if the real strength of mortar is like, in this case, it was about 2 megapascals. So we have 0.2 for uniaxial tension and 2 megapascal in pure uniaxial compression of mortar. In that case, I could use a CFD equal to 0. But in this case, I'm increasing the compressive strength in an non-physical fashion by a factor of 3. So in this case, I put 3 back here. So increasing this 3 will decrease the latency angle to match the exact one that I would have obtained using the real compressive strength. Okay. So if you run this simulation, you will see, and by the way, you have 3 models. So the first one is using the old damaged TC3D. The one in the middle is using the new ASD concrete without using the CFD factor. And this one is the latest one. So ASD concrete 3D with the new CFD factor. So if you run this one in the monotonic test, you will see this output here. While you will run the analysis, you will see the monitor that will be monitoring in real time. So in the dashed line, you have the experimental test. The green line is the TC3D, so the old model, without using the CFD factor. So the same model, but with a dilatancy angle calibrated for concrete, which is not fine for mortar because you increased unphysically the compressive strength of mortar. You will see a higher shear strength due to the excessive confinement. Now, setting up the CFD factor to correct the fake scaling of the uniaxial compression of mortar, you will see a better result here, which is matching the one of the damage TC3D. It's not exactly the same because we use slightly different uniaxial laws for tension and compression, but overall the behavior is the same. So you may say, why do you want to use the ASD Concrete 3D for in place of the old damage TC3D? Is that, well, it is a little bit more robust, but it behaves better in cyclic behavior. And in fact, here I have another test which is cyclic, which is exactly the same as this one, but instead of using here, if you go into the applied load, instead of using a linear ramp, I will be using a cyclic one, which is this file here. Cyclic. This one is the exact same model. The only difference is that I'm using a cyclic pattern. I'm just doing some cycles to show you the differences between the cyclic behavior of the damaged TC3D and the new ASD Concrete 3D. So you run this one, it will take a few minutes, but the output that you will obtain will be this one. So once again, let's compare them all. So as we have seen before, the ASD Concrete 3D without the cross damage factor is overestimating the behavior, so I don't want to see it now. What the real problem that we had with the damaged TC3D at the beginning is that it didn't have the plasticity part, so it was purely damage model. But the real problem was that it was overestimating the damage in cyclic behavior. Now, I don't want to go into the details, but the problem is how we handled the tensile and compressive surface in the 2-parameter damage model. With the new ASD Concrete 3D instead, this doesn't happen. So you have a nice shear-like cyclic behavior with all this pinching that you typically see in this kind of models. And as you can see, it soon returns onto the backbone. You have a bit of cyclic damage accumulation, but it was not as exaggerated as in the damaged TC3D model. So that's the reason why we are migrating to the new ASD Concrete 3D. Okay, so just keep in mind is that if you plan to use the ASD Concrete 3D for a material which is not exactly like concrete, and for that I mean where the ratio between compressive strength and tensile strength is about 10. So if the difference is more than that, you have to pay attention that you may overestimate the dilatancy of this material, so you can work with the CFD factor to have a proper dilatancy parameter. Okay, so it's fine with this model. Oh, of course, you also have the results, so you can see what happens, because it's not just a problem of overestimating the global strength, but you can see also what's going on. Let me go here. The webinar, if you open the output file, you will see actually the difference in terms of also cracking pattern. So if I go here and I plot, let me put a little bit more here. So first of all, let's see the displacement, okay? So as I said here, I was overestimating the latency of the model, and you can see that under increasing cycles, you can see a much larger expansion of the wall, which was unphysical for this kind of material. But you can also see a difference in the crack. So in this micro model, crack mainly go through the mortar joints, and few cracks go into the bricks here. In this case, you can see a crack that is pretty smooth and going through mortar joints and bricks. Okay, this is simply because the mortar joint is overestimating its dilatancy, so it's being highly confined and it becomes stronger than the brick itself. That's why a crack opens through the mortar joint and the bricks as if it was a uniform homogeneous material. Okay, so you can see the difference. Instead, with the old damaged TC3D and the new ASD Concrete 3D with the cross damage factor, you see a similar cracking pattern. Okay. Okay, so now let's go to the next item. Okay. So the next item will be, the zero-length contact ASDimplex, which now can model cohesive zones. Now, actually, this one is a work in progress because we are going to add this new feature directly in OpenSys. We didn't have time to put it in OpenSys, so we created a simple automation in STKO that combines the contact element with other uniaxial material to add the cohesive part to the contact, okay? So what I mean, the ZeroLengthContactASDimplex can only be used to model pure contact, okay? So normal and frictional contact, but it doesn't have an initial tensile strength or an initial cohesion that can model, for example, a thin cohesive layer made of a material. For example, people cannot use this one to model mortar joints in masonry models. So some of the users asked us to implement also these cohesive zones together with the contact element. We are planning to do it in OpenSys. We didn't have time now, so we created a simple workaround in STKO, but we will soon implement it in OpenSys. So what we have done now is to create an automation in STKO that if you choose to model the cohesive zone with the contact element, what STKO will do behind the scenes is to duplicate the zero length element, and one zero length element will have the pure contact, and the other one will have only a constant cohesive part plus a tension cutoff, okay? So putting these two together, like two zero length in parallel, you will see the behavior that you need. So it's actually like summing the pure more Coulomb with zero initial cohesion plus an offset, which is the pure cohesion given by the second zero length element. So this is what is done behind the scenes. Now, how it works in STKO. So you can open now the third example, ASD contact cohesive. I did two tests, one for the normal behavior, one for the tangential behavior, so you can see how it works. So let's start with the normal one. This is once again a 2D model. You have, this is a simple benchmark. So you have 4 points, 1 and 2 points here and 2 points here, okay? Among each one of them, there is a zero length element, okay? Now they are in the same location. That's why you can see 2 points here plus a zero length. They are in the same location because they are initially in contact. Okay, so on the left side, we have the 1 zero length for the pure contact. And on the other side, we have the new one. So the zero length contact plus the cohesive band. How can you model it? Well, it's pretty simple. At the beginning, you only had, with the previous version of STKO, you didn't have this new feature, okay? So this one is a pure contact, where you choose the dimension of your problem, 2D or 3D, normal and tangential stiffnesses, which are like, in this case, penalty values, friction coefficient, and few other things, okay? Local axis, the integration algorithm, if it is distributed or not, I already talked about it. Okay, so this one we give pure contact. If you want to create also a cohesive zone, you can switch on is cohesive flag, and the STKO tool will allow you to choose 4 parameters. So the first 2 are related to the tensile part, so the initial tensile strength and the fracture energy for the normal behavior, okay? So in contact, you will see a behavior which is like infinitely stiff in compression and with a zero strength in tension. Now, in this case, the tensile behavior will be instead an elastic behavior up to the tensile strength, then a progressive exponential softening with this specific fracture energy, okay? The same thing for the cohesion. So you can choose the initial cohesion and the fracture energy for the cohesive part, okay? But this one will behave in shear, so we will not see it in this example. Okay, so boundary condition, I simply fix the bottom, and then I fix the top in shear, because here I'm only trying to analyze the normal behavior. And the loading condition will be on the 2 top nodes. I will apply a vertical displacement. A unit vertical displacement, because then I will use this cyclic pattern to apply a cyclic non-symmetric loading protocol up to a maximum of 0.3 units. Okay, so boundary conditions, the imposed pattern, and then I have two monitors. Okay, one is monitoring the left-hand side behavior, so the pure contact, and the other is monitoring the cohesive behavior on this side. So if I run the analysis, well, you can run the analysis now. I already ran it. You can see, you can just run the monitor, which is here, contact cohesive, normal. You will see this output when you run the analysis. You switch on multiple, and you will see in red the behavior of the pure contact. And in this case, you are plotting the normal displacement versus the normal force. And as I said, well, in this case, it should be infinitely rigid, but I used a finite value just for the sake of representation. Anyway, elastic penalty behavior in compression and zero resistance in tension. So when the contact is opening. If you model the cohesive zone instead, you also have, so let me switch off this one. If you model also the cohesive zone, the compressive behavior will be the same, but the tensile behavior will have this initial linear elastic behavior and progressive damage, okay? And this is according to the FT and GT that you assign. Now, if you go on the other folder, tangential test is exactly the same model, so just 2 points. Well, 4 points, 2 springs, normal, pure contact and cohesive, but in this case, I'm just fixing the bottom. On the top, I'm applying an imposed displacement, in this case, in the X direction, so to apply a tangential slip. But before that, I want to apply a vertical force. Otherwise, the pure contact will not show any strength because the pure contact does not have an initial cohesion. So I applied an initial vertical force of -10 units. And in this case, I'm using a 0.5 friction angle. So I should see a shear strength with that force equal to 5. Okay. On this and on the left-hand side, instead, I should see also the cohesive part that is progressively damaging. So once again, well, in this case, the analysis are two. So I first apply boundary condition, I apply the vertical force. I do the analysis for the vertical force, and then I apply the horizontal displacement, and I run the analysis for the horizontal part. And if you switch on the monitor, you can see the behavior. You can see both of them. So in red, you have the pure contact, okay? So it goes up to 5, and then it activates a sliding. And in this case, instead, you have the same behavior. So 5 as a final residual plateau, but at the beginning, you also have this overstrength here, 5 of cohesion. So 5 plus 5, you have 10 as initial strength, and then this progressively go to 0 cohesion, so a 5 residual stress, which is given by the pure Coulomb contact, okay? And that's it. So at the moment, you can play with it if you need to model a contact, which is not a pure contact, is a contact with a cohesive band between the two contact bodies. As I said, this one is not exactly a material in OpenSys, but what I've done is simply, so instead of creating just one single element, what it does is that for each contact element, it creates another zero-length element with two materials, one for the tensile behavior and one for the compressive behavior, okay? Now, by the next version, we will implement it directly inside OpenSys, so you will not need to do this trick here. But from the user point of view, you are just creating one element. It's just STKO that creates this automation behind the scenes, okay? Perfect. So we are fine with this one. Let's see what's left. Okay, so the next one will be, well, the initial strain and parallel materials. So as you know, in OpenSys, you have many wrappers, okay? Most of them are uniaxial wrappers. Now we are trying to add the same wrappers also for the n-dimensional material. Now, for example, initial strain and parallel materials were available only for the uniaxial material. Now we implemented the same for the three-dimensional ones. Now the parallel material is I'm not going to explain it. It's very simple. It's just summing the effect of multiple materials. I want to talk about the initial strain element, the initial strain material wrapper that can be used also to model creep and this kind of effects. Okay, so let's, and you can see an example here, 0.4 init strain. Before I go on, I want to see if, yeah, we already have some question. I will answer them soon. Okay, let's go back here. So let's open the folder with the fourth example, which is init strain. Now here you can find two subfolders. The first one is the simple one, which is a simple benchmark that I will show you, and the other one is incremental. Now the point with this material, these wrappers, is that they allow you to give the initial strain as an input, which is fine in most of the cases, but sometimes you may want this initial strain to grow in time in an incremental fashion, okay? Especially if you have, either if you're doing dynamic analysis or if you are using nonlinear material model, applying the whole initial strain at one time can be either wrong or can give you convergence issues. So let's start with the simple approach just to explain you how it works. So in this case, it's a simple 2D model. I'm not modeling anything real here. I'm just using a simple concrete 3D model, okay? Two-dimensional analysis, okay? So a two-dimensional plane stress element. And I'm wrapping the concrete model inside another material where I want to apply initial strain equal to 0.001. Now, what is this epsilon 0? Is one value that I will use for all the three direct components. So what I'm doing is that I'm applying a volumetric strain equal to this one, okay? Now, since it is an initial strain material, like the uniaxial one in OpenSeas, what the material does inside is that it sends to the original material, the strain coming from the element plus the initial one. So just to give you an idea, if you apply a positive volumetric strain, your element will shrink. Otherwise, it will expand, okay? So now in this case, I want to simulate a shrinking effect, and I want to apply a deformation of 0.001, okay? Now, in this case, the only boundary condition that I'm using is a pure fix on the X displacement here and a pure fix of the Y displacement here. So I'm just fixing the translational and rotational rigid body modes, but I'm not fixing the deformation. So at the end of the day, what I will see that my element shrinks exactly of the amount that I put here without introducing any stress or damage into the original material, because the element is free to change in volume, okay? So if you run this analysis, you can just open the output, which is in init strain simple. Okay, let me just put a smaller grid. And I want to increase the deformation a little bit more. Okay, so what you will see is that even if I did many time steps, the deformation doesn't change. It's just shrinking from the initial state to this point, okay? Why? Because I plainly assign this material with an initial deformation, okay? So by default, OpenSeas applies this initial deformation all at once without taking care of the time step. So in this case, it was fine because in this example, even if I'm using a nonlinear material, this model here is free to change in volume. So it doesn't introduce any strain in the material itself. But if you do another example, which is the one that I put here, incremental. So if you close this one, and if you go in incremental, and then let's say you want to model something a little bit more real. So for example, in this case, I changed the boundary condition by fixing X and Y in all these corners. For example, what can happen in slabs, okay? They are not exactly fixed, but they are attached to the columns. So let's say they are restrained. So if I apply an initial deformation to this one will try to shrink in this way. Okay, now it is not free to simply change in volume, and it will create a crack pattern on these sides. Okay, so it will induce damage at this point. Now, what's the problem? Since I know that this kind of boundary condition will induce some damage, I cannot actually apply this one all at once. So what I do is to put 0 here as an initial strain. Then I create a region, okay? And in STKO, the region have this extra feature to write the element onto a list in Tcl. So in Tcl, I will have a list with this name. And now I can create a custom command, which is a small Tcl script that I can put here. And in this function, I can reference the list of elements that I want to use to update the parameter. I can reference some extra variables set up by STKO that just will give me the current time. And from the current time, I can get a certain percentage of my analysis. And based on the percentage, I can update the initial parameter of my material, which is EPS0, to a value which is the reference initial strain times the percentage of analysis. So basically, it will, before each time step starts, because now I can create this procedure. If I append this procedure into the list of custom functions that STKO will call before every time step is analyzed in OpenSys, I will change the parameter just before the time step is started, okay? And at each time step, I will apply an increasing value of the initial strain, which is the percentage times the reference initial strain, okay? And then I decided to do an analysis, I think, with 100 time steps. Okay, so if you run this analysis and you load the output, you have it here in incremental. Okay, this is what you're going to get. So let's increase a little bit more the deformation. Okay, now this one is a little bit exaggerated, but what it is doing is that now that you have a nonlinearity, you can apply the initial deformation step by step. Okay, so that the damage is induced step by step, it's not suddenly, so you can actually model the propagation of fracture. Now, in this case, it's very localized because it's a simple example, but it's a way to show you how you can update certain material parameter within the analysis, okay? You just have to write a simple Tcl procedure that will be called either at the beginning or at the end of the time step, okay? So this one is another feature that we have in STKO. Okay, so we are done also with the material wrappers. Let's see what's next. Oh, well, this new feature is actually nothing special, but it's very useful because a lot of people, when they are trying to do a real-life building in OpenSys, they have this problem with the mass of beam elements. Because in OpenSys, modeling the mass or the self-weight of shells or solid element, it's relatively easy because you input the mass density directly inside the material. And so the element in OpenSys will automatically get the lumped mass matrix from the mass density and the volume of the element. The only exception in OpenSys is made for beam elements. For beam elements, you cannot assign the mass density inside the material. For example, inside a uniaxial material, and then the fiber stress will integrate the mass. Instead, in OpenSys, you typically assign the mass of the beam directly inside the beam element. Now, from the theoretical point of view, it is equivalent. So let's, for example, let's close this one and open the auto edge mass example. Now in OpenSys, since, for example, if you create a fiber material with a uniaxial material, you cannot assign the mass density here, so the fiber section will not be able to integrate the rho of every material over the cross section. So you don't have an automatic way to guess what is the mass per unit length in an automatic way. You have to do it manually. So as long as you're doing a simple example like this one, where you have only one cross section, you can simply go into your beam element, activate the mass value here, and here you enter the mass per unit area. But imagine you have 100 different cross sections. You have to create 100 different finite elements because each one of them have a different mass. And the same for self weights. Okay. So many users asked us for creating an automation, okay, to save some time. So what we did is a simple condition, which is called auto edge mass. Okay, here you have two of them because there are two different ways of converting them into self-weight. So the idea is that you go under condition, mass, auto edge mass, okay? And here, what you do is to simply apply the raw of the material, because unfortunately in OpenSys, the raw for a beam element cannot be automatically obtained from the material model. So you have to put it here. But then STKO will take this one, and for each finite element that it has in this model, it will try to guess what is the area of the cross-section. So provided you are using cross-sections that have the concept of an area, for example, an elastic cross-section or a fiber cross-section or a rectangular fiber cross-section, then I can get the area from those cross-sections and multiply them by the mass density and obtain the mass per unit length, okay? So at the end of the day, I'm still creating many different masses, but from the user point of view, it's just one boundary condition. And if you want, you can also convert it to load. If you want to convert it to load, you simply switch on this checkbox. You specify the components of the acceleration vector. Now, in this case, it's simply in the vertical direction, so I put minus 9.81 in the z direction. And you have to just specify how you want to convert this mass into a self-weight. So either using the lumped load approach or the LA load approach. Now, typically you can use the LA load approach, but if you are not doing it for beams, but for example, you are doing it on the edges of shells, then you may want to use simple nodal loads. But the results will be pretty much the same as far as you discretize your elements, okay? In general, the distributed load is better if you're using force-based elements. But they will converge to the same result when you refine the mesh, okay? And also here you have the output, but yeah, it's not necessary to show it now. It's simply to explain that now it's much easier to model mass and self-weight on beam elements when you have like a real-life building with different cross-sections. Okay, so now we are done with the examples that are here in this folder. Okay, so you have only these 5. There are a few more things that I want to talk about, but they don't need a file. So I will just show you how they work. So the first one is the new auto constraint handler. Okay, so let me open a new file. So as you know, in OpenSys, you are responsible for defining how the analysis handles the constraints. Okay. So by default, or in the previous version of OpenSys, you only had plane constraint, Lagrange, penalty, and transformation. I already talked about the differences between them. The two main ones that I've been using, they are either the transformation method or the penalty one. So typically the transformation method is better. It's because it reduces the size of your system because it works on eliminating single point constraints or transforming multi-point constraints, but typically it reduces the size of your system and it enforces exactly the constraint. On the other hand, there is a problem with the transformation is that many times you apply conflicting boundary constraints, boundary conditions. Sometimes you do it because of a mistake in your layout. Sometimes you do it just because you cannot do otherwise. So for example, sometimes you have a constraint node, which must be the retained node in another constraint equation. And you don't have a way to create a simple multiple constraint layout. In that case, the transformation method will not work. And so I suggest users in those cases to use the penalty approach. The penalty approach has the advantage that it can enforce any kind of constraint, even if they are conflicting. The only problem is that the constraint is not enforced correctly. And you can, if you don't pay attention to the values that you have here, you may have an ill-conditioned stiffness matrix. Now I explained in other webinars how to select these values. And then another problem with the penalty method is that typically when I use the penalty method is because of how I need to handle multi-point constraints. But for single points constraint, it's actually overkilling to use penalty method because single point constraints are very easy to handle with the transformation. So you can simply remove the degrees of freedom. So what we decided to do is to implement a new constraint handler, which is called auto. What it does. So single point constraints are handled using the transformation method, okay? While multi-point constraints are handled with the penalty approach. And then, so you have an advantage. You remove a lot of degrees of freedom, those related to the single point constraint. If you have multi-point constraints, you don't have to worry about the overlapping constraints because in that case, we use the penalty approach only for the multi-point constraints. And also in that case, we give some automation to the user. So the user can either choose to enter a user-defined penalty value, okay, so 1 to the power of 18 or something less, depending on what is the stiffness of your model. But if you are not sure about how to calibrate the penalty parameter, you can just go with the automatic approach. In the automatic approach, as it is written here in the documentation, here you don't have to enter the final penalty value. You just have to enter an order of magnitude. So how much the penalty parameter should be larger than the stiffness matrix in the proximity of the constraint. So in this case, I'm using 3 order of magnitudes, okay? So for example, if I find a typical stiffness value under my constraint, which is like 1 million, here I will use 1 million times 10 to the power of 3, okay? So I will increase the stiffness only on that side automatically. So it's very easy to use. You can either go with the user-defined approach. You define the penalty value for multi-point constraint and you get rid of single point constraints because they are eliminated. If you're not sure about that value, you go with the automatic parameter, okay? So simple as that. You don't have to worry about other things. Then we also added the uniaxial version of the ASD Concrete 1D. Also here, I don't need to explain anything because you can just go into uniaxial material, uniaxial, ASD software, ASD Concrete 1D, and you can see that the parameters are exactly equal to the ASD Concrete 3D. You just have some missing parameters which are only relevant for a triaxial state of stress. So of course, in this case, they are not relevant. So I simply remove them. But the theory is exactly the same. I think here you should go to the OpenSys documentation. Yeah, the theory is exactly the same as the ASD Concrete 3D. If you go to the documentation, I also did some tests to understand how the plastic deformation, the damage parameter work. Okay, so you can model different things with the same material. But the idea is that is the exact uniaxial copy of the three-dimensional material. So nothing special. Instead, this one is a new material, or better, it's not a new material in OpenSys. It's an automation that we have in STKO, and it's an automation that we create for creating a bond slip model according to Model Code 2020. And it's not a new material in OpenSys because actually we take advantage of the ASD Concrete 1D and we create 3 instances of ASD Concrete 3D and we put them in parallel. So this is one of the nicest things about OpenSys. You can use simple building blocks to create new material models. So the ASD bond slip actually gives you a simple input. For example, if you are familiar with model code, you will find this ASD bond slip. If you are familiar with model code, you will find this parameter familiar. Otherwise, you have here the reference where we took this from. So with few parameters like the failure mode that can be either splitting or pull out, the bond condition that can be poor or good. Also here you go to the proper reference and you will see what it means to be a poor or good bond condition, if it is confined or not, the compressive strength of the concrete material, let's say like 30 megapascal, and the clear distance between ribs. Now in real life, it is on the order of centimeters. Now we'll put it a small value, like just 1 centimeter, just because we obtain a better graph, just for explaining. Something else that you need to know is about the units, because since this one is based on national codes, you know that in national codes, most of the equations requires the input to be given in a certain unit system. In model code, they want the FC to be given in megapascal, but we don't want the user, we don't want to force the user to use megapascals throughout the model. So if you don't want to use megapascal, let's say you want to use kilonewton meter, for example, you can put 30 E3 here, and you can simply say that you're not doing it in megapascal, but you're doing it in kilonewton meters. Okay, so you just change the unit system that you're using for FC and for the displacement here. Okay, but in this case, I want to use plain megapascal, so let me go back to millimeter Newton and 30 megapascal for compressive strength of concrete. So for example, the first one will be the best performance is given by the pull-out failure mode with a good bond condition. So if you do a test, like a monotonic test, I use like 1000 steps and I want to push it a little bit higher than the clear distance between the ribs, like let's put 12 millimeters. Okay, so this one is the behavior that you have, as it is described in the FIB model code. It's a parabolic first branch, which starts at an approximately infinity stiffness, then it progressively degrades up to a residual plateau, then a softening, okay, and then a residual plateau. So this one is the behavior of pull out with a good bond condition. Now, if you switch to poor bond condition, you will simply see that you have a lower strength and a lower ductility here. So if this one is about 14, if I run the test again, I'm about at 7 with a lower ductility also here. But the shape is the same, because with the pull-out test, the shape dictated by the model code is an initial parabola, and residual plateau, and then temporary plateau, a softening branch, and then a residual plateau. If instead the rebar is very close to the cover, then you may want to choose the splitting condition. Okay, in splitting condition, we can start with the best one, like good and confined with stirrups. Well, in this case, you will see that you don't have the residual plateau, but actually the tau split will intercept the initial parabola before reaching the plateau. Okay, so you simply go with this parabolic first branch, then a premature failure that directly puts you into the softening branch at residual plateau. If you are not confined with stirrups, then the model code does not give you this final plateau and also reduces the ductility. You can see that the first part is pretty similar, then it fails directly and goes to zero strength. If bond conditions are poor, then also this tau split will diminish. Okay, so now we are at about 5 instead of 7. Okay, then you have a few other parameters, like if you want to use a tangent tensor or a secant tensor, the integration can be implicit, explicit. You can use eta for if you want to model the viscosity of the material, but these are not important now. And by the way, for the cyclic behavior, let me go back to the good one. So pull out and good bond condition. I want to show you how the cyclic behavior works. So let me go to cyclic symmetric linear increasing. Let's do, for example, 10 cycles, 1000 subdivisions. Let's do a test. Okay, so as given by the model code, we calibrated the unloading stiffness to be 0.6, the maximum tau. It is provided by the model code, and by the model code, they say that you need to have this plastic part here, then this recovery here, and then you reload on the other side. So you basically have a frictional residual part, but all this plastic deformation can be recovered upon load reversal. So also the model code gives you the details about the cyclic behavior of this material. As you can see, it's pretty different from the ASD concrete 3D, but just combining 3 different materials, we can obtain, because you know the concrete, the SD concrete 1D material, you can define any point for the backbone curve. So you can actually adapt the backbone curve to any kind of behavior. Okay, so here I just combined 3 of them. One concrete that has only a tensile resistance and 0 compressive one. Then I did another one which is exactly the same but only in compression, and then a final one that defines the residual plateau. Putting them together using a parallel material gives you the final behavior. Okay, and I think that I'm done with this. Yeah, is the bond slip 1D. I will talk about them, these new features, when they will be ready. So I'm done with these examples, and now we have some time for questions. Nicola Tarchio, thank you to you, Nicola. Okay, so if you have any other question, we have another couple of minutes. Oh, and by the way, the next webinar will be, Aiden, I think, later in January, right?
That is correct. We will close out the series for this year with this webinar and let everybody enjoy the holiday season that's coming ahead of us, and we'll get started with January.
Perfect, thank you. Okay, so if there are no other questions, please enjoy the new version of STKO. Thank you everyone for taking part to this webinar, and see you to the next webinars next year. Thank you everyone.